All right, good morning, everybody. Today is another Codeforces round, so it's a terrific morning, in fact. And it's round 686, which is a palindromic round. So all of these problems will 100% be about palindromes. I don't know, not actually sure about that, haven't read any of them. But yeah, I'll be competing in it. And if you want to see my thought process, you can watch the screencast of me solving as many problems as I know how to. And then solutions to all the problems I know how to solve will be at the end of the video. So if you're looking for solutions to something, you can see that. Also, I think Neil is putting on a stream after contest to talk about what's going to happen there. So if you're interested in that, you can check that out as well. That'll probably be going on right about now if you're watching this video right as it comes out. But anyway, let's get into the contest. All right, so special permutation. You're given an integer n. Permutation of length n. Yep, we know what a permutation is. You want to find a permutation p of length n so there is no index where it's in the right position. So offset it by 1 is the solution. Okay. That's problem A. On to problem B, unique bid auction. You got it? There's a game called Unique Bid Auction. Read more about it here. Let's simplify the game a bit. Formally, there are n participants. The ith participant choose number AI. The winner of the game is such a participant that he chooses a number that is unique and minimal. Find the index of the participant who won the game. So nobody wins, index 2 wins, index 4 wins. Seems pretty easy. Let's do it. And then it does this. Int array A equals big array of size n. How big can these things be? Yeah. Array counts gives new int array and 100. All right, so now zero, L equals -1, for int I and A. If counts at I, it's got to be integer. All right, for int I equals 0, I is less than n, and I plus plus. If counts of this, counts at A at I, is equal to 0, or equal to 1, and best equals -1, or best is greater than at I, then counts, or then best equals, should be A at best is equal to this, and best equals I. This out, best equals well, just best, yeah, equals -1, otherwise print best plus 1. Seems good. Did I just delete it? Good. All right, submit problem B. On to problem C. We'll listen for the result. All right, we got it. You're given a sequence A consisting of n integers. You want to transform this sequence so that all elements are equal. It contains several occurrences of the same element. To achieve this, you want to choose some integer x that occurs at least once and perform the following operation any number of times. Choose some subsegment and remove it. You're not allowed to choose a segment that contains X. More formally, you choose some contiguous subsequence and remove it. After the removal, the number of elements to the right of the removed subsequence changes. The numbering of the elements changes. Yeah. So we just try it for all numbers, I guess? Yeah. Okay, so this is going to be a little bit messy to code, but we can, for each number, have a list of all of the occurrences of it, and then count that, and then just print whatever's minimum. The elements go up to n. So we'll make all of these 0 indexed, then this can go up to n. Yeah, these are 1 to n, so that's fine. And these go up to n, and now opposite I equals new array list. And now for each of these, occurrences at a at I dot at I at int try some array list integer a and then some int n. Okay, int text equals max value for array list. Try with each of these arrays, and then we print the best answer at the end. So how do we count for a particular array list? Well, it's going to be sorted for us here. So we need to increment anytime there are 2 adjacent things that don't differ by 1. Also if the first thing isn't 0, and also if the last thing isn't -1. This thing right here is not equal to the next thing, and we have to pay one more thing for it. Otherwise, right, so if these 2 elements, if there's like something between these 2 elements, then we have to pay for it. We have to remove everything in between. If a dot get 0 is not equal to 0, then count plus plus. If a dot get a dot size -1 not equal to n minus 1 plus plus. I think that should be fine. Let's try it. Nope, not fine. Nick 0 out of bounds for length 0. Yeah, okay. So if a dot empty, return integer dot max value. 0, 1, 1, 2, 3. Sounds good. We're just flying through these. Alright, we got it. Problem D. Number into sequence. You're given an integer n. Find a sequence of integers such that each integer is strictly greater than 1. The product is equal to n. This thing is divisible by the previous thing for each I. K is maximum possible. Can we not just, oh, each is strictly greater than 1. I see. Yeah, so this one requires a little bit of thought, but I think it's still pretty easy. Let's bring up whiteboard and I can explain my initial idea. So you have you've got something that looks like 2 to the 5th times 3 to the 3rd times 5. Maybe this is what your prime factorization looks like. If this is the case, then you want to pick 2, and then 2, and then 2, 2, 2. So these first 5 numbers will all have 2. Then, yeah, 5 is the most you can pick. You can't pick more than 5 numbers, because once you start picking your prime number, you have to pick it forever. Similarly, you'll put your 3s here, and then your 5s here. So yeah, that's the idea. It's easier to build this thing backwards because we can iterate through each prime. So we'll try some prime factor, like 2, see how many times it appears, and add this to all of these things. And also this length will be at most like 20, well, like, I don't know, maybe like 40, I think. So the length won't be very big. So yeah, you choose X at the beginning, can't change it after. Yeah. So that's the idea for this problem, I think. Let's try it. $5,000 test cases. We can solve each one in 10 to the 5th. It's 5 times 10 to the 8. Whoa. Oh, the sum of n is small. Okay, that's fine. So yeah, how are we gonna do this? Long n equals this. Long remaining equals n. For long prime equals 2 prime times primes less than or equal to n prime plus. Yes, this will be a long array. Yeah. So now, what do we need here? Long array, prime equals new long array. We'll just make it 60 big just in case. Fill times with 1s. So now all of these elements occur once. And we have all of these primes. Okay. So if remaining mod prime is equal to 0, probably be a while loop. then remaining divided by equals the prime. And times will be 0 times plus plus. Or, okay, factors, I guess we'll call it, to avoid name conflicts. Yeah, so then that's fine. So after this, we need to say for I equals 0 is less than factors I plus plus times at I times equals the prime. And now times at 0 times equals whatever is remaining, because this will be one more big factor. All right, what do we print? How many things there are first, and then what they all are? Okay, let's this out. Well, max equals 0 is n at least 2, good. Max equals max.max is maximum 1. Max equals math.max of max and the number of factors. Okay, so we print the max first, then we print each of the elements separated by spaces, and then we print a new line. Looks good to me. Several answers, you can print any. Okay, 2 times 3 times 3. Yeah, let's verify this. 2 times 6 times 30 is 360. 2 is divisible by 6, 30 is also divisible by 6. Or 6 is divisible by 2, okay. This number is a big prime check, and then this number is another big prime check. Looks good. Yeah, I think we're fine. Got it. All right, number of simple paths. Next problem. You're given an undirected graph consisting of n vertices and n edges. So there's one cycle in it. Calculate the number of simple paths of length at least 1 in the graph. Note that paths that differ only in their direction are considered the same. You have to answer T independent test cases. Path in a graph is blah, 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 blah. Okay. Yeah, so in a tree, this is an almost tree, or some people call it a Cthulhu graph. And what is that? Well, if you've got a tree, maybe your tree looks like this. You have n choose 2. So n choices for the first one, n minus 1 choices for the second. Divide by 2, because you count each pair in both directions. So you've got n choose 2 paths that you can choose, because if you have 2 elements, you can only go from this element to some other element. Now the difference here is that we're adding one more edge. So we add this edge here. And when we do this, we introduce a bunch of new paths. So let's draw some stuff here. So we can have multiple things in the same tree like this. We can also have different things in different trees. So I'm pretty sure, what is a simple path? Such that each pair, okay, simple path, such that all vertices are distinct. So yeah, so the ones that don't count are things like this. Like that wouldn't count. But also that means, as a side effect, two things that are in the same branch of this. So we've got this loop, right? Here's the loop. If you pick two nodes that are in the same position in the loop, there's only one path between them. But if you pick any other two nodes, right? So maybe you pick this node here and this node here. You've got two paths. You've got the path in the tree. Then you have the other path, which uses this new edge. So the answer is going to be n choose 2. N choose 2 original paths times 2 minus like the sum of n choose 2 in subtrees. In subtrees. So all we have to do here is extract this cycle. So what's a good way of doing that? Well, if we do a DFS, pick a random node, do a DFS, and we keep going through some node that isn't our parent repeatedly, then we'll hit a cycle. We can just pop from the cycle. Maybe it's easier to just do a DFS and then pop from a stack. Yeah, I guess. Okay, well, what else do we need? We need to know the size of each subtree. Oh, we need to know not the size of the subtree, but like the size of each of these nodes. Or I guess we could just use another disjoint set. Yeah, we can do another disjoint set. Okay. Should we read the next problem? Yes, this one's probably easier. What is the next one? Given an array of n integers, let min be the minimum value among some range, continuous range, max be the maximum value along that range. You need to choose 3 positive integers, x, y, and z, that sum to n, where the min of 1 to x is equal to the min of x plus 1 to y, which is equal to the max from the third range. Okay. So the min, or the max equal to the min is equal to the max. In other words, you want to split the array into 3 consecutive parts, blah, blah. Among all such partitions, you can choose any. I see. Yeah, I guess let's just code up E. It'll maybe take a while, but it shouldn't be too bad. So we wanted a disjoint set. Interesting. I'll have to look at that in a minute. All right, we also probably want a node class. And then, yeah, array list node adjacent. We'll just make this a Boolean in cycle false node parent. Yeah. Okay. And also int subtree size. So I don't think we need this disjoint set at all even. Should be fine. Okay. Node from array deck node SDK. So, I guess we also want a Boolean visited. Usually false. How does this DFS work? So if we're visited, then pop from cycle. Return. Otherwise, visited equals true. And we want to visit all of our kids that aren't our self. Yeah, so for node n in adjacency, if this is not equal to from, and then .dfs, from this, same stack, stk dot add last this, and stk dot remove last this. I'll remove last. Yeah. So now we should add last in the beginning, or it doesn't matter because we will be in the cycle. So while true, we'll pop it earlier, but it shouldn't matter. Yeah. Cycle equals true. Yeah, so this is fine. Okay, so we can do our DFS. What else do we need? I said we wanted a disjoint set. Probably helpful to have, to be honest. Let's just get it. Makes things easier to think about. Alright, find does this union. This size part is what's tricky, so let's figure this out actually. Well, So now in this case, size at A plus equals size at B, and in this case, size at B plus equals size at A. Okay, so we've got our disjoint set now. Yeah. All right, cool. Let's actually solve the problem. Now we've got our stuff ready to go. Int n equals this. Node array nodes equals new node array n. This just builds our graph, so we should be good there. Then we need to do a DFS. So nodes at 0.dfs from no one to new array deck of nodes. So we DFS, okay. Then what stuff is set in the cycle is set. Then we need to make our disjoint set. Long n paths equals n times n minus 1 divided by 2 times 2. Shouldn't be necessary, like that's actually totally redundant because this number is definitely going to be even, but anyway. Yeah, okay, I think we're good. I think we're good. So the number of undirected paths, yeah. So it's this. Then we need to subtract out some stuff. So for node nn in nodes, for node adjacency in nn.adjacent, dj.union, nn.id, and adjacent.id. Union all of these things. Now we should be good to go if we want to read them. So Boolean array processed is new Boolean array n. Okay, so this is if both of these things. Okay, so if adjacent is not a new path, the beginning of a new path. Yeah. If adjacent dot in cycle is false, then union me with him. Good. Okay, so now we want to see what we've processed. So for int I equals 0 less than n I plus int add equals dj dot find I. Process this thing already, then continue. Otherwise, we have processed this. And now we just need to subtract it. So n paths minus equals the dj dot size at this thing times dj dot size at this 1 over 2. I think that's it. I'm so used to doing trees. This is a graph. Really? Okay. Well, let's just do one test case then, see what's going on. So maybe we can say, yeah, what is going on here? What do you mean array next set of bounds exception 1? Oh, this is 3. Okay, 3 and 0. 0, 1, 2, then we get to 0. Why are we in 2 again? Zero null, then 1 from 0, 2 from 1. We should return. What? Oh, I see. Yeah. Okay. If in cycle, then return. Oh no, I'm off by something. Okay, let's look at the second case. 1, 2, 2, 3, 3, 4, 4, 2. 1, 2, 2, 3, 3, 4, 4, 2. So we have 1, 2, 3 pads, 4, 5, 6. There's 6 by default. Plus we have the answer is 11, right? And I'm printing 12. Yeah, so I'm not finding these two are in the same group. Why not? none of the nodes are in a cycle. Why not? They totally are in a cycle. Is being in a cycle. These are false. Oh my goodness. I am kind of silly. Does that matter? I don't. Maybe it matters. Yeah, it doesn't matter. Okay, that took way longer than it should have, but that's fine. I think we should be good. I'm using longs, right? No, I'm not. Okay, good, good. Not too many test cases, so we should be fine. That took half an hour, or like 20-something minutes. Very long. Are we gonna TLE too? What's the time limit? 2 seconds? Okay, we're good. Alright, last problem. Last problem. You're given an array of n integers. Ah, yeah, this one. This is an interesting problem. I like this. It's like tricky enough, not super obvious. Seems kind of like sweepy, you know, like data structures-y. Yeah, okay, so prefix min, is it prefix min or prefix max? Prefix max, also suffix max. These need to be equal. And then there's something in the middle. This is the middle min. So we can brute force this prefix max. Then this will be a continuous range, which we need to binary search. And now this is a min, right? So as we increase it, then this will decrease. So we can binary search this part for where in the continuous range it is. So that's an n log n solution. And then verify the middle min with an RMQ. Okay, so that's kind of overkill, maybe? Do I need, should I put away the big guns? We don't need an RMQ, I don't think. Well, it doesn't hurt. Yeah, I might as well just do it. Okay, easy problems, easy problems. Let's get my range minimum query over here. We don't need low memory because we're doing n log n queries anyway. Got an RMQ, good. This will be range min. Do we want range min? Minimum value. Yeah, we do want range min, okay. All right, so then we have, it's multi-test case again. N equals this. right. Now what's our array? Okay, int array prefix maxes is new int array n, suffix maxes equals new array n, prefix maxes 0 equals a 0, suffix maxes at n minus 1 equals a at n minus 1, I equals 1, that's less than n, I plus plus, prefix maxes at I equals math.max, prefix maxes at I minus 1 or a at I. And this goes from n minus 2 to greater than or equal to 0, decreasing. Suffix maxes equals math.max of the suffix maxes of I plus 1 and a of I. So we have these. We also want an armq. So we can do range minimum queries on this. And now for int L equals 0, L is less than L. We also need to get all of the first time and the last time that the max is a particular element. How big can these values be? Values are up to 10 to the 9. Long variable names are coming back. Okay. For int I equals 0, less than n, I plus plus. Last time suffix max is dot put suffix maxes put I. Same thing, but first, and we go backwards. Okay, so for int L equals 0, L is less than n, L plus plus. I guess it needs to be, so n needs to be at least 3. Okay, so now L plus 2 is less than n. So we need to say, we need to do some stuff. So int prefix, or int value will be prefix maxes at L. Right. So now int like min, the min binary search value, will be math.max of L plus 1 will have to be in the middle, so L plus 2 is the first it can be. And the first time suffix max is this value. And max equals math dot, well, just equals last time suffix max is dot get or default value default 0, or default, I guess, -1. Okay, so while min is less than or equal to max, this is a slightly different version of my binary search, but this works. Yeah, so this is outer. We might have to continue from that. In mid would be min plus max over 2. Okay. Yeah, so if rmq dot query from L plus 1 mid minus 1. This is equal to value. That means that this range works. So we print yes, and then the 3 numbers. So sys out L plus 1 space, and the middle size will be, int mid size will be mid minus L, right size will be n minus mid. Okay. Otherwise, if armq.query r plus 1 mid minus 1 is less than value, then we do one thing, otherwise we do the other. Good. Okay, so how do these things work? Yeah, okay. So if the thing we queried is too small, that means the max of the middle part is too small. Or wait, what does it mean? It means the min of the middle part is too small. The min needs to be bigger, we need to decrease it. Decrease the size, so then max equals mid minus 1. Otherwise, min equals mid plus 1. And here we continue outer. Here we didn't find anything, so we print no. Yes, 6 to 4. Okay, that's a problem. This mid size is wrong. Min minus L minus 1. 614, 252, 412. Okay, second last one we might be getting wrong. There are probably a lot of ways of doing this. So there's 1, 2, 2. Yeah, that's fine. Nope. Hello. Come back. Okay. Silence is deafening. So if I get this, this will be 2 contests in a row in which I will have had no wrong answers. And I got it. Nice. Okay. Probably not terrible performance then, right? Okay, maybe I don't know. I guess I'm just slow. Yeah, 23rd place, not bad, not bad. We solved set faster than Monogon. This took us a long time. There might be an easier solution to E. But anyway, yeah, not bad. It's good to see a mod's doing it. Like to see that. Rainboy. It's not Div 3 yet, so it's good. I guess Div 3 rounds are Rainboy's specialty because he can zoom through them. All right, so yeah, that was a contest. What did I think about the problems? Let me go through them really quick and discuss my opinions. A, special permutation. Yeah, it was a good A. I liked it. Unique bid auction. That's kind of lame. Whatever. I guess good enough. Sequence transformation. Yeah, I don't know. That was whatever. I didn't love it, but it was an okay, easy problem. Number into sequence. This was, I guess this was a pretty classic like math problem. It was not bad. It was like interesting, I think. Yeah, so I liked it. Number of simple paths. This was very implementation heavy unless there was a better way of doing it. If there was a better way, then maybe it's a good problem. But I guess, yeah, it wasn't bad. And then array partition. This was a good problem. I really liked this. How quick did my submission run? Very fast. Okay. Yeah, so I did like problem F. I thought it was good. Let's talk about solutions. All right, so special permutation. So you want to make, you've got these numbers, 1, 2, 3, 4, 5, 6, 7, maybe. You want to shuffle them in some way so that no element ends up being in its like same position as its index. So for instance, one way of doing this would be you could do 2, 1, 4, 3, 7, 5, 6. That's one way. And what I did there was I just took these first two elements and swapped them, the next two and swapped them. And you can just keep doing this if it's even, or if it's odd, you just take the last three and you swap them. So that's one way of doing it. Another thing you can do is you can just take all of the elements and you can offset them by 1. So you move everything 1 to the right, then you'll create a big cycle of length n. This one goes all the way to the beginning, like that. Actually, what I did was I went backwards. So I moved everything back 1. Printed 2, 3, 4, 5, all the way to the end, and then at the end I just printed a 1. So my code for that is pretty short. It just looks like this. Print the numbers from 2 to n, then print 1. And that's one solution to problem A. There are a bunch. I think, actually, if you just randomly shuffle the array and just check, that works too. So you could do a randomized solution as well. Because the expected number of things in their right position, I believe, is 1. I believe, on average, you're expected to get 1 element in its correct position if you randomly shuffle them. And there are a lot of times where you get more than 1. So I think for over half of the permutations, they work. So I think if you just shuffle, chances are in like just a couple tries, you'll find something that works. So I think that's a valid solution as well, if you can't come up with something. All right, problem B. Unique bid auction. Yeah, so this is a super boring problem. So you literally just have to implement it. So you see what numbers are chosen at most once, and then you find the person who is like with the lowest bid who picks something that's only bid once. So in order to see how many times something is bid, we can store for each number how many times does it occur. So I go through each element in the array and then increment how many times it occurs. And then I find whichever thing is smallest that occurs only once. So I look through all of the counts, and if this thing does occur once and not more than once, and it's smaller than my best, or I haven't found a best yet, then this is my new best. And then I just print the answer. So that is problem B. Yeah, it's just implementation there. Problem C, sequence transformation. You have some sequence. Yeah, you want to remove some stuff. So the idea is, okay, if you've got some sequence, like maybe you have 1, 2, 3, 1, 2, 3, 1, then the things you're going to have to remove will be these continuous ranges here. If you remove 1s, if you remove 2s, you would have to remove things before the first 2, between these 2s, and after this. If you remove 3s, you'd have to remove these pieces here. So what we can do is say, let's say we know what number we're going to remove. Then every time we have like some continuous block that separates these, where this block is non-empty, so it contains at least one thing in it, we're going to have to spend a move to remove it. Also, if the last thing isn't the first element, or isn't the last element, we need to spend one move to remove this block. And if the first thing isn't the first element, we need to spend a move to remove this one. So that's, I guess, some idea on how you can handle it. And if you try every element, then your total runtime for one particular element will be the number of things that are equal to that value. So here, if we try 3s, it'll take us like order 2, because like order number of 3s basically, because we just have to iterate through how many 3s there are. And if we do this across all numbers, every number will be counted once, so the total runtime will be order n. The code for that is we get the occurrences of every number. So I make a bunch of different array lists, one array list for every value. Then for each element in the array, I mark its occurrences in my list of occurrences array. So now I have this list of all occurrences of some value. And if I ever have 2 occurrences of this value that are like next to each other in sorted order, but differ by more than 1, that means there's some different value between them. So I would have to remove that, and then I'd also have to remove the first thing if like the first thing in the array isn't this, and then the last thing if the last thing in the array isn't this. Yeah, you could clean this up even a bit more by starting these arrays all with a -1 and ending with an n, and that would allow you to remove these 2 cases if you'd like. Okay, cool. That's problem C. On to problem D, number into sequence. So I explained this problem a bit when I was solving it, like I explained the solution a bit, but here's the idea. Let's say that you've got some number. For instance, maybe you have 2 to the 5th power times 3 to the 3rd times 5. Whatever number your array starts with, let's say it starts with like just the number 2. Every other element in your array needs to have a factor of 2. So this has to have a factor of 2. This could have a factor of 2 squared if you want. Maybe it could have a factor of 2 cubed, but it could also just have a factor of 2. So we'll just give it a factor of 2 for now and not worry about it. So we'll put one factor of 2 for each of these elements. And like we can't have more than 5 elements here, because our first number has to be not 1, right? The rest of them have to have a factor of 2 in them. So our answer has to be 5 or less. We can definitely make it 5, and I'll show you how to make it 5. But we know there isn't a better answer that we're missing out on, because the biggest it can be is whatever our biggest exponent is. Okay. Cool. So how do we make it 5? Well, we put 5 2s down, and now in the next turn we have these 3s, so we'll put a 3 in each of these positions here. Now we have 5s, so we'll put a 5 in this position. So now our array is going to be just this. It'll be 2, and then 2, and then 2 times 3, which is 6, 2 times 3, which is 6 again, then 2 times 3 times 5, which is 30. And this is our array. Now you'll notice that since we only add, like as you go from left to right, all you do is add new factors, then these new factors will not like you'll always be divisible by the thing to your left, because you always have all of its factors. And then what are the other constraints? That it's increasing? Yeah, it is increasing. Well, I guess that's not really a constraint even. The constraint is that the product of these is equal to this number. And that's true because the number of 2s here is just 1 for each 2 in the original number. Same thing with the number of 3s and the number of 5s. Cool, so what does this look like? Well, yeah, it's kind of a lot of code all at once. It's not really super well separated, but I can explain what's happening. We store this times is each of the numbers, and then just to make things easier on myself, I actually store this array reversed. So this will be index 0, this will be index 1, this will be index 2. The nice part about that is I can go through these numbers and not need to know how long it's going to be in the beginning, and then I can just like I can keep printing these until the rest of them are all 1s, and then just ignore them from there. So yeah, so this first number here, this first number is going to be the biggest number. So, okay, I should also talk about this, which is these numbers get pretty big. So we need to know all of the prime factors of this number. Since this is a div3 round, it's fine if you don't know how to do that. So I'll explain how you can find all of the prime factors of some number, There are faster ways of doing it, but here you can do it in square root n time. So the key observation is that a number only, like some number n, only has one factor. Like it's got like less than or equal to one factor that's bigger than square root of n. One prime factor, I guess. Why is that? Well, if it has two factors bigger than or equal to square root of n, the product of those two factors will be bigger than n. So what we can do is we know that it might have a bunch of small factors, but it only has one big factor. So if we divide out all the small factors, what we're left with is the big factor. So we can find what that big factor is in square root n time by checking all of the small factors, removing all of them, and now we're left with 1 or 0 things that are big. It might have 0 things that are big. So if you look at the number 16, for instance, that doesn't have anything, like there's no prime factors greater than 4. But it has a bunch of prime factors less than 4. I guess it just has 2 a bunch of times, but yeah, that's fine. I guess 12 is another example, right? 12 has 2 and 3, which are both less than its square root, but nothing bigger than its square root. As a counterexample, or as like something that does have one factor, you can look at the number 17. So 17 has no small factors, but it has one big factor, which is 17 because it's prime. So that's the only thing bigger than its square root. Okay. So that big factor, which we have either 0 or 1 of, that's what I take care of at the end. So I'm going to divide out all of the factors that aren't that big factor. I'll divide them all out, and then I'll be left with at most 1 prime, and I'll use that at the end. So for all of these factors, first I want to start like how many times is this prime a factor? So that's what this factor number stores. Factors number stores. Hard to say, man. Whew. Tongue twister. Okay. But I go through each of these numbers. Now, not all of these will be prime, but each time I have some number, I divide it out as many times as possible from n, which means if you look at the smallest factor of n, that's definitely going to be a prime number, right? So I look at the smallest factor of whatever this remaining number is, and I'll divide it out, and then I'll find the next smallest one, divide it out. So every time this while loop hits, that means this number is actually prime. And also, at the end here, this will be prime as well, because it's the smallest remaining factor. So yeah, so we divide out this number, and then if this occurs at least once, then we set max to whichever is bigger, the numbers less than us, however many times they occurred, or this, which means we can now extend our answer to be this many numbers. And for however many times we need to add this number to the answer, so like we need to mark a bunch of these things as 3s, we need to add 3s to this. I just multiply all of those numbers here in my array by whatever this number is. So now finally, I do this part, which is I just print the answer. So initially I print max, and now since I stored these in reverse order, I print them back to front. Okay, sounds good. Yeah, that's problem D. On to the next one, problem E, number of simple paths. So this is kind of a messy problem, but it wasn't too bad, I think. The idea is you have an almost tree. So you have a tree, but there's this additional constraint, or additional edge in the tree, really. So we have a bunch of nodes, a bunch of edges, and then there's this additional special edge in the tree. They don't tell you which edge is special, but when you have this edge, you've created this cycle here. And now this cycle is, you've got exactly this one cycle in the tree, and from each of these other nodes, you have these trees coming off of them, right? So this part is a tree. You might have a tree that looks like slightly more complicated. You might have something like this. You might have a tree coming off this that looks like this with like some other stuff. You might have an empty tree here, just this node on its own. You might have some tree that looks like this. So now you want to know how many paths are there in this almost tree. And we're going to do that looking at a tree first. So if we have some tree, the total number of paths is n choose 2. So n choices for the first node in the path, n minus 1 for the second choice for the second node in the path, then you counted all paths twice. Okay, but now this additional edge has introduced a bunch of new paths, because for any two nodes that don't come from the same node in this cycle, that means they have to travel across part of this cycle. So if you're going to travel from here to here, or any two nodes in the cycle that are different, you can take the original part of the cycle like this, or you could go backwards and take this extra edge now. So we want to know for each node in the cycle, right, anything in this group can now match with anything outside of the group as well. We want to add up all of those possibilities. So one thing we can do, the way I calculated it, is I said any pair of nodes, there are always going to be two paths between those pair of nodes, except in one case, which is if both of those nodes are in the same subtree group. So it's n times n minus 1 over 2, but then we need to take this number and multiply it by 2, because there are two ways of getting from each pair of nodes. And then we want to subtract the sum of these subtree sizes. So this subtree that I've circled in yellow, that's like one subtree. The sum of like subtree size, choose 2, across all subtree sizes. Because any two nodes in the subtree, there's only one path between them, since we never actually touched the cycle. So that's the math behind it. The actual code isn't too bad. The idea behind this is the first thing we're going to do is find which nodes are in the cycle. So I'm going to do a DFS, and you don't need this toString, I guess. So first I do this DFS, and I store which nodes are visited in the DFS, and also like whether I'm in the cycle. Basically, what's happening here is I have a stack of all of the nodes that I've seen in the cycle, like my call stack. And first I add a node to the stack, and then if this node's at the top of the stack, I remove it. But then sometimes what'll happen is, like when I do my DFS, I make sure that I don't DFS to the same node that I just came from. So I don't go from me right back to my parent, but I might somehow loop all the way around and find another path back to my parent. If I do, that path will be on the stack. So I want to pop it off of the stack and get what that cycle is. And there's only going to be one cycle. It'll only happen once. So this is this is the case that I'm looking for. If I've already visited the node that I'm at here, and I got here a different way, that means I'm back at like the root of the cycle, and I want to pop the entire cycle off my DFS tree. So that's what happens here. I pop it off the tree, and I mark everything in it as being part of the cycle. And I keep doing that until I reach whatever the top of the DFS tree is. So by doing that, I can see what things are part of the cycle. Now for everything not in the cycle, I want to merge these groups together like this, so that I know the size of everything. And I do that right here. So I look at each node, right? So maybe I'm looking at this node here. If the node it's touching is not another node in the cycle, then I merge these two together. So basically I use all of these edges here and merge them all together using a disjoint set. My disjoint set also stores the size of each node. And then once I've done that, once for every node in the disjoint set, once for every group, I subtract out the size of that component. That's how I solve the problem. There might be other ways of solving this, and I had to spend some time debugging because initially for a bit my DFS method had issues finding the cycle correctly. But yeah, that's one way of solving it. Okay, very cool. And then last problem, problem F, array partition. So for this problem, I just kind of brought out the big guns, but here's the here's the solution idea. You have a bunch of nodes. Well, the problem is you've got a bunch of nodes, and you want to find some prefix, some suffix, and then some middle, where the max of these things is equal to the min of these things and also equal to the max of these things. So the first observation is we're going to take a prefix of the max, right? Let's store all of our prefix maximums. If we do that, the max of some set of numbers is only going to increase over time. So maybe this is like the prefix maxes. If we look at the suffix maxes will also increase, but from the back. So the suffix maxes will look like this. I'll do this in a different color, I guess, so that it's easier to see. So that's these things. So yeah, you might even be able to make even more optimizations here. But basically, what you can notice here is, let's say we know what the prefix max is. Then this will correspond to some continuous suffix. So we have some continuous range of suffixes that this could match with. Now, we could like binary search this, basically, that's one idea. But what we're looking for is some time in which the minimum of the middle part is equal to the value of this prefix max. So this prefix max, we already know what it is because we're pretending that we know what this first cut is. So we're going to brute force what this first cut is. This will happen order n times. We're going to fix it. And then for the second half, we want to binary search where the right like split point would be, if there is one. So yeah, the reason we can binary search it is because we know what value we're looking for. We want to see when the minimum becomes that value. We also have like some range in which this max is legal as well. So we want to binary search that range. Okay. So yeah, that's the idea. We're gonna have some range in which this maximum is legal, and then we want to see when does the minimum become legal as well. And we can binary search because as you move this to the right, the minimum will get smaller. So if the minimum is too big, we need to move farther to the right. If it's too small, we need to be farther to the left. And that's the idea. So brute force the left endpoint. We know a range that the right endpoint is valid for. We're going to binary search in that range to find where the middle becomes valid, if it ever does. And if it does, we'll find it in log n time. If it doesn't, we need to do n log n checks in total across everything. Okay, cool. What's the code? So to do this range minimum in the middle, I used an RMQ. If you don't know what an RMQ is, I made an algorithms thread video on it, so you can check that out. And I explain what they are and how to do some optimizations for them in low memory. You don't need the optimizations for this problem, but the video explains how they work, so you can look at that video if you'd like. And what is the code? Okay, so we've got this RMQ. This is literally just copy pasted from Hackpack. This part is the actual code. So we store the prefix max and the suffix max for every prefix and suffix. And we also have this this hash map where I store for some suffix max, when is like the first suffix where that suffix max occurs, and when's the last suffix for that to occur. This is the range, like if I know what the prefix max is going to be, this is the range that I'm allowed to binary search in. Yeah, so I build all of those things. The prefix maxes and suffix maxes are easy to calculate. The RMQ handles it by itself. And then I just store the first and last time I have this prefix and suffix max. So now here's what I want to binary search. So the left endpoint that I'm going to binary search has to be at least my left endpoint plus 2. So the minimum, this min and max, these are the min and max bounds for the right endpoint. The left endpoint is fixed. So I fix it in this for loop. But for the right endpoint, it has to be at least the left endpoint plus 2, because I need the left endpoint to be the left endpoint inclusive for the left range. I need at least one element for the middle. Now this is going to be the right endpoint. So this is the smallest it can be. And for the max, I need it to be in this valid range. This also needs to be like in the valid range because the max on the other side needs to match what I'm looking for. Okay, cool. So now I do my binary search. So this is the case in which it works. So we know the right endpoint is valid because we're looking in this range. And if this happens, that means the middle is valid as well. That means the min along the middle is equal to the max along the two outsides. So we are set here. And we can just print our answer. Okay, last case is if it doesn't work. So now if the middle part is too small, that means we've expanded it too far, because as we expand the middle, it gets smaller because it's a minimum. So like a range minimum. So we want to decrease the size of the middle. We do that by setting the right endpoint to be closer to the beginning. So this is the max right endpoint. We set it equal to the closer to the middle than the left. Otherwise, this is the case in which the left endpoint or the right endpoint needs to move to the right because the minimum was too big. So we need to include some smaller number. We want to do that by expanding our range. And that's it. There you go. All right, so I hope you enjoyed. There are another 36 minutes of competition, but I won't upload this until after, obviously, because I don't want to help people cheat. But yeah, thank you for watching. Hope you enjoyed, and have a great day. Hope your rating went up if it was rated for you as well. All right, goodbye.